In this video, we're going to look at how to use the sine, cosine, tangent, cotangent, secant, and cosecant functions to help us to fill in the blanks of right triangles. And tomorrow and the day after that, we will be looking at how to use the trig functions to examine triangles that might not contain a right angle. Today, we should be able to relate the trig functions to the quantities in a right triangle, and we should be able to use the trig functions to determine the unknown values of those quantities in a right triangle. Now remember, back when we were deriving the Pythagorean identity, that we were able to fit a triangle, a right triangle, with a hypotenuse of 1 in the unit circle. The hypotenuse could be drawn from the origin to the rim of the circle and would have a length of 1. And in this drawing, the length of the vertical side of this triangle would be equal to sine of alpha, where alpha corresponded to the angle in this bottom right corner here. Meanwhile, cosine would be equal to the horizontal leg of the triangle, cosine of alpha. This was true specifically if you had a right triangle with a hypotenuse of 1. Okay, well, what if your triangle's hypotenuse has a length that is not equal to 1? What if your triangle has an hypotenuse of some other length? Let's call it r, perhaps. Well, if you scale up the hypotenuse going from 1 to r, then that will also scale up the lengths of the other two sides. So 1 becomes r, sine becomes r times sine, and cosine becomes r times cosine, if angle alpha is positioned here in the bottom left. So in other words, the length of the side opposite to angle alpha is equal to r, which is the length of the hypotenuse, multiplied by sine of alpha. And the adjacent side to angle alpha, the length of that side is equal to the length of the hypotenuse, r in this equation, multiplied by cosine of angle alpha. And so if I rearrange these two equations, I get the following result. Sine of the angle alpha is equal to the length of the opposite side divided by the length of the hypotenuse. And cosine of the angle alpha is equal to the adjacent side, length of the adjacent side, divided by the length of the hypotenuse. Now, because tangent is defined as sine divided by cosine, what does tangent represent in terms of this right triangle? Tangent of the angle alpha is equal to sine divided by cosine. Since sine is equal to opposite divided by hypotenuse, and cosine is equal to adjacent divided by hypotenuse, if I simplify this fraction, tangent is equal to opposite divided by adjacent. So the mnemonic for the meaning of sine and cosine and tangent in a right triangle is SOHCAHTOA. You'll get people who have never taken a math class or haven't taken a math class in 25 years who know this abbreviation. SO is for sine opposite hypotenuse. CA is for cosine adjacent hypotenuse. And TOA is for tangent opposite adjacent. So SOHCAHTOA is the mnemonic for these three formulas. Now, the amazing thing about these three formulas, SOHCAHTOA, is that they can be used to take a very limited set of information about a particular right triangle and to fill in all of the remaining data about the triangle. So that's what we're going to be practicing doing with the rest of the lecture, using sine, cosine, and tangent, as well as some general geometric formulas to take two values in a right triangle and extrapolate all the values of all the angles and sides. Now, when someone is describing a right triangle to someone else, there are a variety of different ways to give someone data about a right triangle. And the first and most visually explicit way to describe a triangle is to draw the triangle and mark all the locations on this triangle with all the side lengths and all the angles. Now, traditionally, the two angles in a right triangle are denoted by the Greek letters alpha and beta. These are Greek for the letters A and B, respectively. It's traditional to denote the side length that is opposite angle alpha by the Roman letter A. And it's traditional to represent the length of the side opposite of the angle marked by beta with the Roman letter B. And the hypotenuse traditionally is called C. For example, someone says, I'm thinking of a right triangle that has sides of length 3 for A and C is 6. The hypotenuse is length 6. So let's see if we can use just that data to fill in the values of all the angles and all the sides. Now, there are generally speaking 3 tools at our disposal when we're working with right triangles. The first of which is the rule that says that the angles in a right triangle add up to 180 degrees. So in this context, whatever value we find for beta, plus whatever value we find for alpha, plus the right angle in the corner, all those values have to add up to 180 degrees. That's one of the tools that we're going to use to fill in the blanks in this right triangle. The second tool that we're going to use is the good old-fashioned Pythagorean theorem, which says that a squared plus b squared is the same thing as the hypotenuse squared. And the third tool at our disposal is the SOHCAHTOA formulas. As a general principle, to use a formula, you need to be able to fill in the values of all but one unknown. For example, it would not currently be appropriate for me to try to use this formula alpha plus beta plus 90 equals 180 degrees, because at the moment both alpha and beta are unknown, so I would have two unknowns in this equation. However, it would be appropriate for me to use the Pythagorean theorem because I can fill in the blanks right now of both A and C. That means that B will be the only unknown left. There will be a single unknown left in the formula, and therefore I will be able to solve that equation to determine the value of B. So if I plug in the fact that A is equal to 3, and I plug in the fact that C is equal to 6, I know that 9 plus B squared is equal to 36. And therefore, subtracting 9 from both sides, I figure out that B squared must be equal to 27. And therefore, B must be equal to the positive square root of 27. Now, as an aside, why am I ignoring the plus minus that usually shows up in these equations when I am undoing a square? I get to ignore the plus minus because B is an actual side length and therefore cannot be negative. Now, the square root of 27 is perfectly acceptable as an answer, but it's possible to simplify this result. I'll call this optional. If I break down 27 as the product of 9 and 3, then I can break down the square root of 27 as the square root of 9 times 3. And the square root of 9 can be reduced to just the regular 3. So if you desire to simplify, you can find that B is equal to 3 times square root 3. That's optional, however. I'm going to mark this with a box because this is one of the quantities that I need to fill in the blanks of the given right triangle. So, what is left to determine? The thing left to determine is alpha and beta. So I'm looking for a formula that contains either alpha or beta, but I'm looking for a formula where I can fill in the blanks of all but one variable in the formula. So option number 1 is out. I'm going to turn my attention to SOHCAHTOA instead. For example, the SOH formula says that if I take sine of the angle alpha, then that's equal to the opposite side of the angle alpha divided by the hypotenuse of the right triangle. And in this particular problem, the value of the opposite side is equal to 3, and the value of the hypotenuse is equal to 6. So I'm trying to find an angle at which sine outputs 1/2. Now, this angle actually shows up on our reference image for the unit circle. The angle at which this is achieved is 30 degrees. Now, some of you may be thinking, yes, alpha equals 30 degrees is one angle that causes sine to output this value. But what about all the other angles? For example, alpha equals 150 degrees, or 30 plus any full rotation. Note that alpha actually needs to fit inside of a right triangle. So alpha has to be between 0 and 90 degrees. That's what's special about the angles that are in right triangles. Angles in right triangles have to be less than 90 degrees. So I'm going to ignore all these other solutions because they're too big to fit inside right triangles. Okay, so now I've determined the value of alpha. How can I then determine the value of beta? All these options, I think that the easiest one is not to use SOHCAHTOA at all, and is to go back to the formula that says that if you add up all 3 angles in a right triangle, the result has to be 180 degrees. So as a consequence of this, if you take the sum of angles alpha and beta, the result of that has to be the remaining 90 degrees that is not provided by this corner. We can determine that 30 degrees plus beta is equal to 90 degrees, and this, in my opinion, is the best way to determine that beta is equal to 60 degrees. Let's try one more abstract example. In this case, they're describing to me a right triangle where the angle labeled by alpha measures 15 degrees. So I'll make a quick note of that really fast. As well, they're telling me that the side labeled by B has a length of 5. So from this information, let's fill in the blanks. of what is the side labeled A, what is the length of the side labeled C, and what is the size of the angle labeled beta. Okay, now there are lots of different ways to get started on this problem, but no matter what, you need to start by using some formula where you can fill in all but one of the unknowns in the equation. One value that it looks like will be easy to get is the value of beta, because once again I can use the fact that if I take the angle alpha and add it to the angle beta, the result of that should be 90 degrees. And therefore, as a result, the value of the angle beta should be 75 degrees. So we got one of those angles right off the bat, and now what's left for us to determine are the values of the two sides. So I think I might use one of the SOHCAHTOA equations. The SOHCAHTOA equations, generally speaking, have slots for one angle and two sides. So if I pick the correct SOHCAHTOA equation, then for example here, I have arrived upon a formula where I am able to fill in the blanks of 2 out of the 3 unknowns. So cosine of 15 degrees is equal to 5 over c. This would be an equation that I could use to make some headway in this problem. Cosine of 15 degrees, however, this is not one of the angles which shows up on my unit circle reference image. So I'm going to need to use a calculator in order to determine this value. Now this is a situation where you're going to need to be very careful to make sure that your calculator is in degrees mode, because we are coming off of quite a number of questions where we were dealing primarily in radians. So check and make sure that your calculator, whichever one you're using, understands that you're about to enter 15 degrees. So I'll load 15 into the calculator, open the trigonometry menu, and plug that angle into regular old cosine. And it says, okay, the result of that is going to be equal to 0.97 approximately. I am allowed to round my final answer to 1 decimal place. I usually find that it's good practice to round intermediate values to a slightly higher degree of accuracy, especially if I'm working with something like online homework, which can be really finicky. So I'm going to go ahead and maybe even go all the way to the 4th decimal place, 9659. So now, to solve this for c, I'm going to clear the fractions and divide. C is equal to the value 5 divided by 0.9659, which according to the calculator is approximately equal to 5.2 units. Okay, as of this moment we have determined the value of everything except for the remaining side, which is the side of length A. There are a bunch of options at this point to determine the length of side A. You can use basically whichever one works. I think for me, I don't know, I might just pick at random, maybe to use one of the SOHCAHTOA equations. That seems nice enough. For example, if I plug in sine of 15 degrees, sine of alpha, that should be equal to A divided by C, and now we know that C is equal to 5.2. Sine of 15 degrees is equal to 0.2588, and once again I'm just adding a little bit of extra accuracy so that there are no problems caused by me rounding too much too early. And therefore, to find the value of A, all I have to do is multiply the 0.2588 by the 5.2. And so that turns out to be equal to approximately 1.3. That's the approximate value of A as rounded to 1 decimal place. So for a more concrete example, In the United States, there are laws that dictate the shape of wheelchair ramps to make sure that the ramps are not too steep. So in particular, for wheelchair ramps in commercial areas, for example, a wheelchair ramp is built in front of a grocery store, it's required that if you want your ramp to increase by an amount like 4 inches, then the length of the actual ramp has to be 4 feet. In general, however much you want to rise along the ramp's hypotenuse has to be 12 times the rise. So based on this law, let's figure out the angle of elevation for a commercial ramp. So in other words, let's figure out the angle, the maximum angle which is allowed here in the bottom right corner that points toward the vertical side of this ramp. So a sample ramp which satisfies the law is given in the picture above. If we have a vertical rise of 4 inches, then the length of the ramp has to be 4 feet. In other words, 4 times 12 or 48 inches. So what equation could I use to determine the value of alpha? I need a formula that has an alpha in it, but also a formula where alpha is the only unknown. It seems to me like I could use the formula that sine of alpha equals a divided by c. I can fill in the value of a, and I can fill in the value of c in this formula, and all that will be left is alpha, a single unknown that I can solve for. This is a perfect opportunity to use arcsine. Let's plug 1/12 into arcsine and get the angle from that makes this equation true. The angle in degrees, because I'm in degrees mode, cannot exceed 4.78, approximately speaking. This is the largest angle of elevation that is permitted for a commercial wheelchair ramp. You can see that data confirmed on this website. They are specifying that the steepness of the ramp, the angle of elevation cannot exceed approximately 5 degrees of incline, which would be the answer that we got, just rounded to the nearest whole degree. Let's answer another question in this same setting. Supposing that we are building a commercial ADA compliant ramp and we need the ramp to cause us to rise by 3 inches. Now the data in the law says that corresponding to that, the hypotenuse of the ramp has to be 12 times larger, has to be 3 feet, aka 36 inches. But generally speaking, when you're constructing these ramps, what you need to know is whether or not you have enough horizontal space to actually fit the ramp in your design plan. So in this case, how much horizontal space would we need to fit this ramp into whatever construction project we're working on? As always, several different ways to answer this kind of question. One of which would be to use the SOHCAHTOA formulas, now that we know that the angle alpha here in the corner is approximately 5 degrees. But I think my first inclination personally is to use the data about the values of A and C in this triangle together with Pythagorean theorem. Okay. Give me a moment. I'm going to figure out these values using a calculator. E squared is equal to 1287, and therefore B itself would be equal to the square root of that, which is approximately 35.9 inches. Notice that because the angle in the corner here is so small, only 5 degrees, the length of the actual ramp and the length of the horizontal side are almost exactly the same. So in a planning project, you can effectively just say, take the rise and multiply it by 12, and that's basically as much horizontal space as we need. So we have an object which is being launched at an angle of 60 degrees. So if here is the ground, we have an object that is being launched at an angle of 60 degrees. We're told that the speed of this launched object is 90 miles per hour. So, hypothetically, if this object was allowed to continue traveling at this speed along this trajectory for an entire hour, it would go 60 miles. Now the question is, how fast is the object moving upward? 90 miles per hour is the object's overall speed. How fast specifically is its vertical speed changing? If we consider just how far it moved upward in that same hour, how far would this object move upward in that same hour? Now, in this sketch, we've ended up accidentally creating a right triangle. I could use, for example, one of the SOHCAHTOA formulas, which says, say, that sine of 60 degrees is equal to the opposite side length divided by the adjacent side length. Now, looking at our unit circle reference image, sine of 60 degrees is equal to root 3 over 2. And therefore, if I clear the fractions, the object covers a distance of a equals 90 times root 3 over 2 miles in 1 hour. Vertical speed. According to my calculator, the object's vertical speed would be approximately equal to 78 miles per hour upward. That concludes today's material. We talked about the SOHCAHTOA formulas for right triangles. Then we used those formulas in combination with the Pythagorean theorem and some geometric facts about right triangles to fill in all the unknowns in a right triangle, given just a few pieces of data about that triangle.